to my talk, and so I'm really happy and lucky to have this chance. So, anyways, so I'm Yuuka Kanakubo. I'm a weekend item. I joined weekend items in October as a weekend Berkeley fellow. I am actually going to moving to the Berkeley soon if I get the visa on the right time, and then I move to Berkeley from the beginning of January. So before I go to Berkeley, I just want to share my passion, like what I am interested in and what I am excited about. So what I am excited about is quark-gluon plasma, which is the hottest consisted of quarks and gluons. So imagine that you have an ice cube on your phone, and then if you want to study the dynamics of the H2O molecules, maybe you want to melt the ice cube into the water. Then maybe you can shake it, you can shoot a bullet inside, and then that's basically how you study the water, how viscous it is. And we want to do the same thing in quark-gluon plasma, the super quarks and gluons as well. So quarks and gluons, those are the minimal particle which is building up all the matter surrounding us and also ourselves as well. But if you want to study the super quarks and gluons, just heating up the matter it's not sufficient. So you need actually 2 trillion degrees. So it's really, really high temperature. So just to give you some feeling, so the surface of the sun is just 1,000 degrees, and inside of the sun is about like 10 million degrees. So you know that the energy scale that I am talking about is like really, really high. So this kind of liquid was filling the early universe just after the Big Bang. So now, like, can you imagine how this kind of soup looks like? Is it like a water or is it like a honey? Actually, this is a big problem and the quiz that we are trying to solve. And unfortunately, from the first principle calculation, this kind of dynamical properties you cannot really get yet. So and also, of course, in order to make a scientific conclusion, you need to based on the observations, right? And that's why we have this relativistic heavy ion. So I gave the catchy name on my title, on my talk. So the recipe for the soup of quarks and gluons. So there you go. So you have ingredients. So you need to prepare a pair of the heavy ions, such as lead ion, gold ion, uranium, xenon, and so on. So the species doesn't matter actually. So it's better if you have larger heavy ions. Then so you place those heavy ions inside of the accelerator, and then you start the acceleration. And well, usually for the particle accelerator, you have this like ring-shaped pipe where the particles are getting accelerated. And for example, the Large Hadron Collider, LHC, is sitting in the CERN. So this has almost like 30 kilometers circumference. So it's really, really huge. Then make sure that your heavy ion gets accelerated up to almost speed of light, actually like 9.9. So it's almost almost close to the speed of light. So if you are sitting at the laboratory and then you see the heavy ions, it looks contracted like a pancake because of the gamma factor, which is almost like 10 to the power of 3. And after the collisions, some energy like quarks and gluons will be deposited in between these outgoing nuclei. And once it gets equilibrated, this is here you go, like you have quark-gluon plasma, the soup of quarks and gluons. Well, and because it's the recipe, so it roughly takes like 10 to the power minus 15 seconds to get your soup after the collision. And then the tips is that as I said, it's better if you use the large and heavy ions. And if you accelerate the particle with high energy as possible, and then it's better if you have the central collisions as possible, because it makes you to, it allows you to have a lot of energy available, and then there will be a lot of interactions among those quarks and gluons, which helps the system to be equilibrated. So, but unfortunately, the thing is that you cannot really see or taste or smell the soup that you made in the laboratory. That is because, not only because it's dangerous, obviously, but also it's because of the nature of the strong force working between the quarks and gluons. So at the energy scale, when you have the measurements, after the collision and after the formation of plasma, the system is evolving like with the relativistic speed. And once it's evolved, the temperature of the systems goes down. And at some point, at this, like the energy scale becomes very low, and quarks and gluons are reconfined into the hadron. So what you can actually measure in this heavy ion collision is the final state hadrons. And you only know, so you basically have a list of the final state hadrons, and you know the momentum and the energy, which allows you to calculate the mass and you know what kind of particles are produced. Anyways, and then this is what makes it actually complicated and also interesting in this research, because what you want to actually know is the quark-gluon plasma, but you need to see the history of trace the information of the quark-gluon plasma, which was embedded in the final state hadrons. So since we cannot really see the quark-gluon plasma form, and then how do we actually know if there is any this kind of matter formed in the system? Well, there is no silver bullet. What we are doing is we analyze several different observables which can indicate the possibility of having quark-gluon plasma. So here, there are lots of the QGP signals, so-called, but here I would like to just tell you the two QGP signals. The first one is so-called strangeness enhancement. The name looks, the sound fancy, but it's basically the ratio of the number of the particles produced in the systems. So if you have a set of the particles, the list of the particles produced in the systems, maybe the first thing that you would do is just counting the number of the particles, right? Then, let's say you have this highly accelerated nuclear colliding, and let's say 10% of the total energy is deposited in the systems, and then it becomes the QGP, quark-gluon plasma. Can you guess like how many particles are actually produced? Well, so at the leading order estimation, maybe what you can do is you assume that, okay, so you have quark-gluon plasma, which has a volume V. And maybe you can assume that the quark-gluon plasma is homogeneous, so it can be characterized with this one, the constant temperature. Then if you know the statistical thermodynamics, you can calculate the number of the particles, right, for the different species. But of course, in the reality, it's not that simple. Actually, of course, some particles are coming from the non-equilibrated systems, and also there would be some hadronic interaction which deviates from the thermal equilibrium. And also, well, of course, the quark-gluon plasma is not homogeneous. The temperature will be fluctuating in different locations and so on. But from the experiment and from the theory side, it has been shown that this kind of like simple estimation actually works. It's not that bad to estimate the number of the particles. So from the experiment, it has been shown that, okay, so the vertical axis is the ratio of the number of the particles. The number of the omega hadrons per the pions. It means the relatively heavier particles over the light particles. If you see the proton-proton collisions or proton-lead collisions, which is considered as a very small systems, which is not enough to create such a hot plasma, you don't get that much heavy particle produced because it's difficult to produce the heavy particles in vacuum. But if you see the event where the central collision is happening in the, let's say, leaded collisions, and actually you see this significant enhancement of the ratio. So you start to get more and more heavier particles in the system. And this value is shown that it's consistent with the estimation that you can get from statistical thermodynamics. So it will tell you that, okay, indeed, the system created in the heavy ion collision is under equilibrium, right? Then the second observable, second signal that I'm going to talk about is so-called elliptic flow. It's basically the correlation between the collision geometry and the direction of the momentum of the final state hadrons. So here I draw some pictures. So let's see this reaction from the angle of the beam axis. And the left one, the ion is coming towards you, and then the right one is going away from you. And then you have the photon plasma formed in the overlapping region. So if you have this kind of function where you have a certain impact parameter, so it's not like the head-on collisions, but it has like certain overlapping area, and then it has this kind of almond shape. So maybe you can imagine how this kind of system flows, right? So if you have this hot matter, the almond shape sitting in the vacuum, then what hydrodynamics tells you is that the particles would be accelerated in the direction of the pressure gradient. And then if the pressure gradient is bigger, and then you have more accelerations. So in this case, the expansion happens like this. And so from this kind of event, if you measure the particles from this angle, it's called azimuthal angles. And then if you plot the particles as a function of this phi azimuthal angle, you actually get this kind of pattern. So you tend to get more particles at the pi equals 0 and then pi equals 5. And then once you get this kind of pattern, the frequency, and then you want to expand it with the Fourier series. And so you see that the second order Fourier coefficients is actually dominating as a result. So this is called B2 in our field, which is also referred to as the elliptic. And if you plot this B2 as a function of centrality, how central those heavy ions are colliding. So the left-hand side is when those are kind of like really peripheral. And if you go to the right-hand side, the centrality will increase. It starts to get overlapping each other. And finally, you have this like the really central collision. And then the B2 behaves like this. So first of all, you don't have that much the matter created, but once you get to have this almond shape and then you have more of the B2 signals, then but if the system gets really symmetric like the circle, and then you don't get that much like B2. So this is observed in the experiment. So from this, this kind of result can be described with the hydrodynamics as well, and then you cannot really get that much B2 from the weakly coupled, for example, the Boltzmann dynamics. So that's why people say that, okay, the system created in heavy ion collision is actually strongly coupled liquid. So finally, the thing is that like how we are actually simulating. So we are actually simulating this heavy ion collision from the modeling of the heavy ion itself and until the very end of the evolution in full 3D and as dynamical as possible. So I think the time is ticking. So for the details, if you want to listen to, if you want to know what I am actually doing, what we are actually doing, please come to my seminar, which will be on the next week. So 10th of December, Tuesday. So thank you so much.
Okay, thank you very much, Yuuka, for very enjoyable talk. So any questions or comments? Go ahead.
This sign of collision, particle collision, but heavy ion collision is deal to using time or mathematics. What do you use to analyze?
The collision. So in heavy ion collision, the thing is that so we in the theoretical model, the initial condition is actually not known. Usually people use the PQCD. So you just pick up the quarks and gluons inside of the nuclei, and then you calculate the scattering with the PQCD. And we assume that the quarks and gluons deposited in the collision, they get thermalized. And then after that, this evolution of the quarks and gluons is usually described by the hydrodynamics, relativistic hydrodynamics, where the interaction, all the interaction is incorporated through the lattice QCD at this energy scale.
Is number correct? I think 1 Fermi is 10 to the minus 22 or 23. 10,000.
No, sorry. It's probably. No. Sorry, it's a mistake. It's a mistake. Sorry, it's a mistake. It's a mistake. It's not a second, right? It's Fermi. It's actually meter. I wrote it.
Oh, meter. Oh, okay.
So it's a second. In second, it's.
So meter inverse of
Yeah.
Big the recipe is 10 to the minus 19 meters. That's a very confusing recipe.
Sorry. I wrote the.
It's not time.
It's not time. Thank you for the correction.
Yeah, my question is that in this short time scale and short, space, the volume, why hydrodynamics works, and what's the?
But why hydrodynamics works? I think it's it's a big problem why hydrodynamics works. But empirically, it's just that first of all, the motivation to have the hydrodynamics to describe the system because we wanted to study the Kogon plasma, which is supposedly under equilibrium, right? And then we want to study that in the relativistic heavy ion collision. So I think it's just conceptually right to try to describe the system with hydrodynamics, the dynamics of the equilibrium matter. And then the second thing is that empirically, you know that actually hydrodynamics works to describe the particle reductions observed in experiments, such as the particle ratios and then also particle spectra. So it has like exponential shape. So you can actually see that the thermalized picture is actually working. But it is actually really a good question, and then people are working on it to justify if it's really possible to apply the hydrodynamics as a theoretical picture in such an extreme situation.
So following the question is I just don't know. Like the event seems extremely wild and like volatile. So typically, even if hydrodynamics work, it's very difficult to simulate it if it's extremely non-equilibrium, right?
No. Well, so it's
I'm just saying, like, at this time scale, is it considered equilibrium phenomenon, or is it like
phenomenologically considered as the equilibrium. And then the equilibration time is still unknown. And then that's why like people are actually working on the non-equilibrium physics, and then some people are trying to actually extract the equilibration time. They like at which time you can actually apply the hydrodynamics in the early stage of the relativistic heavy ion. So, honestly speaking, so I don't have the good answer for that because it's one of the big questions. Maybe if you have some idea, we can probably discuss them.
Yeah, because like, I mean, it's like you create a plasma and the plasma goes away. But within a short period of time, you think that the equilibrium has formed.
Well, so usually in phenomenology, we start applying the hydrodynamics from 0.51 Fermi, and then we continue the hydrodynamic evolution until the certain temperature, but it's almost like 10 Fermi. But as I said, it's not like justified. The theoretical picture is not justified, but it's just that it just makes sense to use the hydrodynamics to describe the system because that's what we really wanted.
Did you agree with the data, or?
Yes, from hydrodynamics in heavy ion evolution.
The question, should quark-gluon plasma behave like honey or water? And so it seems that from your talk, it's like a honey.
Actually, it's like it's more like water. It's more it's almost ideal hydro. So the viscosity is very small. And
so viscosity is very small.
Viscosity is very small. This is what is actually predicted by the 8050, but also this. If you simulate the evolution of quark-gluon plasma using the zero viscosity, actually it works. Describe, for example, this like V2 or other. Yeah, thank you for.
Okay, thank you.
Okay, Yuki Fujimoto have a question from Zoom.
Yes. Thank you. Yeah, it's a bit related to the previous questions, and maybe it's a bit technical. But so I often hear the statement that the hydrodynamization and also the thermalization is a different condition. And as you showed in this, in the blackboard, you showed the strange enhancement that somehow requires the system to be described by grand canonical ensemble, and I guess that's refers to maybe a thermalization. And does this imply thermalization as well, or I'm not familiar with this, but
it just tells you that the system is almost under thermalized, but the thermalization and as long as I know, of course, in order to apply the hydrodynamics, it should be locally equilibrated.
Yes.
And it should have the proven, and also it should be the isotropic in a momentum space. So this is actually not really enough to justify the hydrodynamics in the heavy ion collision.
Okay, I thought the applying grand canonical ensemble requires a stronger condition than the that you can apply the hydrodynamics. You need, I thought, the global equilibrium of
Yeah, this is let's say So this is very simple model, right? So but okay, so these two are actually really like different things.
Right. Yeah. I understand. But yeah, I just wanted to confirm that, like, if whether the thermalization is required or the like just the hydrodynamization is required, which is
everything is, yes, it should be stabilized. It should be isotropized in
okay.
order to apply the hydrodynamics. And then, yeah, to justify that, I think there are a lot of things to do.
Okay. Yeah. Thank you.
Well, actually, I have two questions, but one is technical and one is general. So let me ask only one general question. Well, since today we have many biologists, so I want to ask this question. Well, quark-gluon plasma is realized in a very extremal condition. And why it is important is because, well, it was realized at the early universe. And also, well, understanding this extremal status of matter is important to understand the microscopic dynamics and well, something like that. So my question is not to you, but to biologists. So are there any similar phenomena of life in extremal? And that's my question to anybody that has an answer. No. Not only physically extremal, but in the biological sense.
And like volcano?
Well, that's of course one physically extremal condition, volcano or very high temperature, high pressure, or whatever it is. Well, not only that kind of physically extremal, but also where in a extremal situation, where something like where many lives gather together or whatever it is. And I wonder if that kind of research will help to understand the biology. That's my question to all of you.
One thing we're doing is so we can sequence ancient people like the Neanderthal, or like the sister species that existed. And that's kind of, and then they mix with our ancestors. And that's kind of an extreme situation. So hundreds of thousands, millions of years diverge. And you can actually learn something about what it means to be human through that. So it's like an extreme scenario, if you like, or two sort of separate groups meeting, which can reveal something about us today.
Right. Oh, okay. Yeah, that's very nice.
And not just in humans, but any other species you could think of.
Well, yeah, so yeah, I wonder how extremal condition is very extremal. So we usually think that that is realized in a very specific condition. But sometimes like this, where it's quite important. So, yeah,
but hydrodynamics is actually applicable to cases where it's not very extreme.
Yeah. Well, that's but not extremal in the sense of technique.
Yeah. I mean, I think blood flowing is more relevant to hydrodynamics.
Collective behavior of animals and
Maybe I'm wrong, but yeah, so I'm a biologist, and so when the horizontal axis, the size of the system, I mean, when the life emerged on Earth, so maybe proton-proton interaction is sufficient. So certain, I mean, dense and larger, molecular weight molecules are necessary for some interaction. And also the density, maybe larger.
Yeah.
So that's a very naive idea. Some kind of soup.
You mean the origin of Earth?
Yeah. How about Kumamushi for experimental situation in life? I had varied experiment to measure quantum entanglement between Kumamushi.
Really?
Yeah. I had
Quantum effect.
quantum entanglement between state of two Kumamus. Yeah. I'm not sure. Yeah.
And now
Very good. Yeah, I have very such expression. Yeah, maybe even if we call extremely, they can be alive.
Yeah, right. So in extreme condition, such as
Can I ask what equations you use to simulate thermodynamics? Is it
So that was in the hydrodynamics.
hydrodynamics? Is it Boltzmann's equation or Navier-Stokes?
No, it's just that one mu T mu nu. T mu nu is decomposed with the mu nu, the for velocity, and then and then plus, and then it should be combined with equation space, the relation between the pressure and the.
So you don't have a viscosity term.
Viscous term there is a viscous term in the hydrodynamics.
So it's like a Navier-Stokes.
Yeah, well, the second order hydrodynamics. Well, you can actually include. Well, it really depends on, like, there are lots of hydro models which only simulates for example, ideal hydrodynamics, the first order, and then second order. You can include the viscous terms and so on.
So are the parameters of the equation from?
The parameters are the viscosity, and then what people actually do is, so you set the viscosity as a parameter, and then you compute this two, for example, and then you compare it with the expected parameter, and then you perform the Bayesian analysis. So then you constrain the viscosity, and then that's what people actually do, and then that's how people concluded that okay, the QGP has a very low.
I see. Is it possible to do it with latitude? Like first principle calculation, can it give you parameters of
like
people doing the calculation of the viscosity, they're trying.
Is it possible? There's a time problem at the.
The viscosity, I mean, it's an inverse problem. It's a sort of so you have to calculate the real-time correlation function.
But isn't this also at finite density?
Oh, this is only finite temperature, no variable.
Very high viscosity on a high temperature is easier to calculate. There is severe some problem for low temperature.
So this is finite temperature, finite density.
No, very density.
Very density. I see.
Well, I also want to ask if the state is hydrodynamized, it means that the quantum effect inside of this state is small.
It's incorporated in the lattice QCD, I would say.
Yeah, because I mean, is it possible to simulate the real-time dynamics using some quantum computer things to very
people, I think there were some people talking about that in the last PNL weekend workshop.
Because I think quantum computer can to simulate the stabilization process and to see whether it's
I'm sure that there was this talk. I think there are people working on that in PNL. But yeah, that would be really interesting, I think.
Since the temperature is so high, so the effective dimension is reduced. So does it make the simulation easier or difficult?
Okay, I think I didn't follow what you meant by the
at very high temperature where the time direction becomes more. But since it's a real problems and the real dynamics of
okay.
It doesn't make the simulation easier.
Okay, so now I think I'll call it, and thank again Yuuka for very interesting presentation and the subsequent discussions. Thank you very much. And I'll just stop facilitating, and you can come to Yuuka in person here or attend the seminar next week, and you can